Today's going to be 34-1, and we're going to be looking at trig graphs, and we're going to be taking a look at the different parent graph functions, and more specifically, the concept of amplitude when it comes to these. So today's objective, we're going to identify the different parent graphs for sine, cosine, and tangent functions, and then understand what amplitude is from trig graphs. Now, in order for us to graph sine, cosine, and tangent functions, we're going to utilize the unit circle, and we're going to take a look at the axes points or the poles. So we're going to focus on these four poles when we're determining our values. So let's begin by focusing on the graph of cosine, which is y equals cosine of x. Now, because I said we're focusing on our poles, I'm going to label my x-axis what these values of rotation are. So 0, and then pi halves, and so pi halves, pi, so pi, 3 pi halves, and then it comes back down to 2 pi, and so 2 pi, and then I can do negative rotation, so negative pi halves, negative pi, negative 3 pi halves, and negative 2 pi. So now when I have to go through and I have to label all these different things, what I need to focus on is my cosine values. So if I'm going to say the cosine of 0, well, the cosine of 0 is 1. And so my y value would be 1 there. The cosine of pi halves is 0. And so it's going to be, my y value would be 0. The cosine of pi is negative 1, so then my y value would be negative 1. And then the cosine of 3 pi halves is 0, and so my y value would be 0, and then back to 2 pi, my cosine of 1, or 2 pi is going to be 1. And then I can also do negative rotation. So if I rotate negative pi halves here, that's going to be 0. Negative pi, it's going to be negative 1. Negative 3 pi halves is going to be 0. And then negative 2 pi, it's going to be 1. And so I can draw this image or this picture, and there's my cosine graph. Now this portion here, this is going to be our parent graph. So basically, when I say, hey, cosine, what's the parent graph of it? In your brain, you need to have this image. Starts at the amplitude, crosses the center line, goes below, crosses, goes back up like that. And so it should look something like that. These values are important values. And so for our parent graph, those important values are going to be 0, 0, pi halves, pi, pi, 3 pi halves, 3 pi halves, 2 pi, 2 pi. So just know that these are going to correspond that way. Now with sine, we're going to use that same process. Everything's labeled on the unit circle as we see, and now I need to go and use or evaluate those values on the unit circle to find those important values. So at 0 degrees, my sine value is 0, and so that's why my y is 0 here. At pi halves, it's 1. At pi, it's 0. At 3 pi halves, it's negative 1. At 2 pi, it's 0. And then negative rotation, that's going to be negative 1, that's going to be 0, that's going to be positive 1, and that's going to be 0. And so once again, I can draw my curve here. Now, one thing that I just want to emphasize with this, these are smooth curves. If you go through and you're drawing your sine and cosine graphs and you're like, okay, there's no jagged jaws of doom. You can't draw sharp curves with this. They are smooth curves. And so make sure that when you draw this, you draw it in terms of that smooth curve. Now this part right here, this is our parent graph. And so once again, we still have those same important values. And so if I were to ask you and say, hey, what's the parent graph? You should be able to draw this type of image, and it'll create that parent graph. Now here are some of the different properties of cosine and sine. The first, they both have the domain of negative infinity to positive infinity. So if I were to take this and I were to smush this under the number line, right, everything gets projected, it's going to be solid from negative infinity to positive infinity. The second has a range of -1 to +1. So for these, if I were to smush them onto the y, smush them onto the y, it's going to be here, and it's going to be solid all the way through till I get to +1. It's continuous and smooth. So remember, there was no jumps, there was no gaps, it was just continuous the entire time, and the curves are smooth, meaning no jagged jaws of doom. We talked about this yesterday. My cosine is even, and my sine functions are going to be odd. So looking at this one here, my sine function, it's odd because if I reflect it over the x and then reflect it over the y, the points will line up. And then coming back to my cosine function, we'll look at this one here. With my cosine function, if you notice, they reflect perfectly over the y-axis, right? I can fold that, and if I fold it, they line up perfectly, and so that's why it shows that they're even. And then the natural period, and I'll talk about what period is tomorrow, that's going to be 2 pi. But if you notice, the distance that it took from where it started to where it ended, that distance is 2 pi. That's why the period is going to be 2 pi. Another way of thinking about period is it's the distance you travel along the axes before the cycle starts repeating itself. All right, so now we're going to define what amplitude is. So if I take a look at my parent function, cosine of theta, all I'm going to do is just rescale it. So instead of it looking like it takes that distance to get to 1, it's just that distance to get to 1. Now the reason why I did that is I'm going to compare that and kind of visually show you what the amplitude is. Now we find the amplitude to be this value in front of our function. So that value is going to be the amplitude. So in this case, if I have the graph of 5 cosine theta, I'm going to say that my amplitude is going to be 5. Now let's see what happens here. And so that is my cosine graph with the amplitude of 5. Now it looks like this got stretched up to 5. This got stretched 5. And if you made that type of assumption, you're absolutely correct. What the amplitude is it's the distance from the center line to the amplitude. And so this distance here, that's 5. This distance here, that's 5. And so on and so forth. Now one thing to note, amplitude is always positive. Or amplitude is never negative. You will never have a negative amplitude. Now you're probably wondering, well, what if I have -3 cosine theta? Isn't my amplitude negative then? The answer is no. We have to consider these separately. That's going to be a reflection over the x-axis. So if you remember from our functions and their transformations, a negative in front of our function means that there is a reflection. That is our amplitude, and so our amplitude is going to be a +3. And then I can determine my parent graph to be a cosine graph. So remember, the definition of the amplitude is the distance from the center line to the maximum or minimum. So let's state the amplitude and sketch each of the following. So there's a few elements that I should be examining here. First, we said that amplitude. So for sine of theta, I know my amplitude is going to be a +4. But now I need to imagine what is my parent graph. And so with my parent graph, we know with sine it's going to start at the center line. It's going to go up to the amplitude. It's going to go back to the center line. It's going to go below, and it's going to end up back at the center line. And it's going to have this type of shape. Now those important values, we said the important values are 0, pi halves, pi, 3 pi halves, and 2 pi. Those are those important values. And so notice it's been labeled 0, that's the first one. Then it goes up to the amplitude, which is a distance of 4 at pi halves. and then crosses the center line again, pi here, goes below 3 pi halves, and crosses again at 2 pi. So next one, 6 cosine theta. So once again, my amplitude is going to be 6, but now this time my parent graph, cosine, that's going to start at the amplitude, it's going to cross, it's going to go below, it's going to go back to the amplitude, and it's going to end up back where it started. And so it's going to have that type of shape. And so same important values, 0, pi halves, pi, 3 pi halves, 2 pi. And so here we go. There's my amplitude. There's the distance to the amplitude. Starts at the amplitude, crosses, goes below, crosses, goes back up to the amplitude. 1/2 cosine theta, my amplitude is 1/2. Follows that same pattern of the parent graph as we move through it. Now this is an example where we might think, is that a negative amplitude? The answer is no. My amplitude is still a positive 5. But visualizing this, if normally sine has this type of pattern, because of that negative, it's a reflection. So this is going to get reflected down, this is going to get reflected up. And so it's going to have that type of shape there. And so if you look at it, see how it goes down first, and then it goes up. So those are just some things to be made aware of. So now we're going to talk about tangent. And the way that we find tangent, if you remember, is we have to use the ratio sine of theta over cosine theta. We're still using those poles from the unit circles. That's why I still labeled everything 0, pi halves, pi, 3 pi halves, 2 pi, etc. But now we're going to use these poles to kind of help us. So for my first set value 0, it's going to be sine over cosine. So 0 over 1 is just 0. And so my y's value is going to be 0 there, so I have a dot there. Here, 1 over 0, well, that's undefined. The way that we say undefined in math is generally with an asymptote. There is one exception, and we'll talk about that later. Here, with pi, I have 0 over negative 1, which is 0, and so I have a dot at 0. At 3 pi halves, negative 1 over 0 is undefined again. And then back at 2 pi, 0 over 1 is another dot. And then negative rotation, undefined, dot, undefined, dot. And so my parent graph for tangent is going to be between here and here. Now you're probably wondering, like, wait a minute, why is it only that part? Well, it's because the period is different. If you notice, if I have dot, asymptote, dot, the graph starts repeating itself much sooner, and so that's why it's going to be smaller. Now this is the shape that tangent is going to get from those dots. It's kind of like a smooth curve that goes that way and a smooth curve that goes that way. And you draw those curves from the dots. No jagged jaws of doom. Now the important values for us is going to be 0, pi halves, and pi. Now, one thing that's going to help us a little bit, okay, it's a person. He can be very dear to us, but Dad's going to help us graph these, okay? And so if you ever forget, how to graph tangent, you got to call on Dad, because Dad is dot, asymptote, dot, asymptote, dot. And so it'll help us kind of remember the pattern when it comes to tangent. Now here are some of the properties of tangent here. The first, it has a domain where x is everything except x cannot be pi halves plus pi k, where k is an integer. Now let's kind of like examine that. Right now, because of these asymptotes, we said that it cannot be pi halves, 3 pi halves, negative pi halves, etc. Now, what this is saying, this equation right here, it's saying x cannot be pi halves plus pi k. Now, because it's saying where k is an integer, well, that means we have to plug in k equals 0, k equals 1, k equals 2, and we also have to plug them in the negative direction as well. But if I start plugging those in, if I plug in where it's 0, I get pi. halves. If I plug in k equals 1, I'm going to get pi halves plus pi, which is 3 pi halves. If you notice, that value is this value is this value. If I plugged in k is negative 1, then I'm going to get pi halves plus negative pi. Well, that's going to give me negative pi halves. That's that value. So it's an equation that we're able to create that's going to be representative of every value that it cannot be. And typically you just want to start with the value, and then whatever the distance is that it takes for me to get to the next value, which is pi, well, we just say it has to be pi multiplied by an integer, and that helps us construct it. This statement here, this is something I'm not going to spend a whole lot of time on. We might have a little bit of time later to analyze what this statement means, but in a nutshell, this is just the union of all of these intervals. And what I mean by that is it's the union of this, union this, union this, etc., etc. And you plug in values for k from negative infinity all the way to positive infinity. Tangent has a range of negative infinity to positive infinity. So if I do project it onto the y-axis, so if I project, it's going to be a solid line all the way from negative infinity to positive infinity. And so that's why the range is negative infinity to positive infinity. It's continuous and smooth on its domain. So on the actual domain, there's no gaps. So between here and here, there's no gaps. And it's smooth. No jagged jaws of doom. We talked about this yesterday. It's odd. And visually, it has that period of pi, because the distance from here to here before it starts repeating itself is going to be pi. So state the amplitude and sketch each of the following. So I have 10 tangent theta. Now my amplitude is none. But let's examine why. This is what my graph looks like, right? Dot, asymptote, dot, asymptote, dot. These are those important values that I was telling you about. Now from that dot, you draw those smooth curves, but there is no amplitude, and the reason why there is no amplitude is because we defined amplitude to be the distance from the center line to the highest, which is the maximum, or the lowest, which is the minimum. So is that the highest point on the graph? Is that the highest point on the graph? Is that the highest point on the graph? The answer would be no to all of those. There is no highest point on the graph because that's going up forever. And so because there is no highest point on the graph, there is no maximum. And so therefore it's kind of almost self-contradictory to the definition. And so that's why there is no amplitude. And so this concludes our lesson. And if you guys have any other questions, please leave them in the comments.